In order to develop an integral formula for area in polar coordinates, let's remind ourselves what we know from trigonometry about the sector of a circle. For a circle with radius r and a sector with central angle theta, the area is equal to 1/2 r squared theta. This becomes our fundamental unit for area in polar coordinates. For reference, in rectangular coordinates, the fundamental unit is the rectangle. In other words, for polar coordinates, the formula a equals 1/2 r squared theta plays the same role that a rectangle does in developing the integral formula in the xy coordinate system. Our formula for area is then going to be, well, in polar coordinates, considering r as f of theta, our delta a sub I is going to be 1/2 f of theta squared times delta theta. You can see that we're building this off the formula for the area of a sector. And this leads us to saying that area is equal to, well, it's going to be a sum as I goes from 1 to n of 1/2 of f of theta squared times delta theta. We're going to take a limit as n approaches infinity. And that result is, of course, going to be an integral from a to b of 1/2 f of theta squared d theta. It's very important to note that in polar coordinates, area is not equal to an integral from a to b of simply f of theta d theta. That works for rectangular coordinates, but not polar coordinates. For an area between two curves, say f and g, let's say f is the bigger of the two curves, the area is going to be the area given by f. So the 1/2 times the integral from a to b of f of theta squared d theta minus the area given by g. And so 1/2 of the integral from a to b times g of theta squared d theta. And combining these into a single integral, we end up with that the area is equal to the integral from a to b with a 1/2 out front times f of theta squared minus g of theta squared d theta. This resembles what we would have done in rectangular coordinates with that area formula when we saw the area between two curves in first semester calculus. So let's go ahead and box up what's important here and here. We'll see how this area integral is applied in a later video, but for now we're going to turn our attention to arc length. Recall that for parametric arc length, we have the formula L is equal to the integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. In polar coordinates, since x is equal to r times the cosine of theta and y is equal to r times the sine of theta, we have that dx d theta is equal to dr d theta cosine of theta minus r sine of theta using the product rule, and dy d theta is dr d theta times the sine of theta plus r times the cosine of theta. Keeping in mind also that the sine squared of theta plus the cosine squared of theta is equal to 1, we can come up with a formula for, or an expression I should say, for dx d theta squared and dy d theta squared, trying to mirror what we have for parameterized arc length. Squaring dx d theta, we get dr d theta squared cosine squared of theta minus 2 dr d theta r cosine of theta sine of theta plus r squared sine squared of theta. Doing the same with dy d theta, we end up with plus an expression that's very similar, except that the respective places of cosine squared and sine squared have traded, and we have, instead of a subtraction for our linear or middle term, we have a plus for our middle term. Those will subtract out. And then in a pattern that we have seen before, if we look at the first expression that we got from both dx d theta squared and dy d theta squared, we can factor out a dr d theta squared, and we're left with sine squared plus cosine squared. In other words, we have dr d theta squared plus whatever we get at the end here, and we have r squared sine squared of theta plus r squared cosine squared of theta. Again, factoring out, we have r squared. What we end up with is that if f is continuous and if r is equal to f of theta, then the arc length, which had been given in parametric form as the integral from alpha to beta of the square root of dx d theta squared plus dy d theta squared d theta, becomes the integral from a to b of the square root of r squared plus dr d theta squared d theta. You know, there's no reason for me to have alpha and beta here. So I'm going to make both of these integrals go from alpha to beta, and now everything matches. And as before, we can box up the result here so that you know it's important.